This information is brought to you by Charles Sturt University.
Hi, this is a video looking at 3 different double integrals and just looking at how you might consider doing them. So this is partly revision and certainly give you a sense of, given an integral, what sort of things go through your mind of how you work out which method you apply. So the first one we've got here is a double integral dx dy where you've got limits specified. So the first thing you try to do is just try to treat it just on its own merits. And so for a double integral where you've got the limits quite clearly given to you, you just try doing it as an iterated integral. So you try the inside integral first. So this one here, so we have to integrate this expression with respect to x first. So that's sin x and x. Problem is that doesn't look like a very easy thing to integrate. So we don't really know quotient rules, etc., and parts or substitution don't really work well with that. So as soon as you get to a situation where the inside integrated integral is difficult, you go, maybe I should try something else. So what other options are there? Well, you could try transforming the region to something else, or changing coordinates. So if it's a certain region, you can try changing coordinates, might fix things up for you. And so the biggest application of that is if you've got something based on circles. Another option is you could try to swap the order of integration. For both of those, it really is useful just to see what the region of integration is. So what we're doing is I'm going to draw a picture of what the surface looks like. So the inside limits here pretty much suggest that x is between y and 1. So I'm going to draw the line x equals y, which is the line y equals x, like y equals x, and the line y, x equals 1. So I know it's between those two curves, essentially. And then I also know that y is between 0 and 1. So therefore it's the bit of the region between y is between 0 and 1. So therefore the region I've got is this triangle here. So this top line is x equals y, or y equals x, same thing. I've got the line y equals 1, and the x-axis are the sort of bounding curves. So it's not a circle or anything bit of a circle, so certainly polar coordinates would not be helpful here. And trying to pick other more complicated transformations is difficult, but you certainly trying to swap order of integration is a useful thing to do here. So to do that, we just need to reformulate this as basically y is being between two functions of x. So if you look at, so previously it was considered being between two functions of so x has been two functions of y. We want to go the other way now. So now we want to do y is being between two functions of x. So the highest y gets is this line here, which is the line y equals x. And the smallest it gets is this line down here, which is y equals 0. Then we have to work out what the range of x's is. And so x is between 0 and 1. And that gives you our new limit. So therefore, our integral, so we'll call it I1 for short, for our first integral, now becomes, we'll swap the order of integration around. So the inside limits now become y is between 0 and x. So we're integrating y first. And the outside integrals, we're integrating x from 0 to 1. And the integrand stays the same. And the whole reason for doing that is now when we do the inside integral of this expression with respect to y is easy, because there's no y's at all. It ends up being just the integral of just y, sine x, on x. And then we have to plug the limits of 0 and x in a second. And after we do that, we'll have to still do the outside integral. So write it down for bookkeeping. So if you plug in y equals x into here, you get x sine x on x, so the x's will cancel out. If you sub 0 into this expression, you just get 0. So it just collapses nicely just down to sin x, which is fantastic, of course. And so the reason for changing the order of integration is to make, therefore, it gets rid of the harder integral. Now you integrate sin x normally, so integral of sin x is minus cos between 0 and 1. Plug in 0, you're getting 1 or minus 1, so minus minus. Plug in 1, you're getting cos of 1. That would be the answer. So something along those lines. And so, just trying to, again, the key thing is, you certainly need to know how to do the integral, but how do you work out which method to pick? And that is, I just tried doing integrated integral first, realised that that's going to be hard, and therefore triggered, let's try and make it easier myself. Let's swap the order of integration around. Let's try another one. This is another integral. This time the region of integration, we're not given the limits directly, but we're given the region of integration separately. So in this case, if you look at how it's specified, it's still specified mostly in terms of how you think of limits. So y is being between two functions of x. And so just sort of natural, if it's specified that way, is to integrate y first between x and 2x plus 1, so between two different straight lines. And then we'll integrate x next. And again, it naturally gives the limits for x. So although it was not written in the same format, it was very easy to translate to in this case. That doesn't mean it's integral straightforward to do, so we're just trying the same trick. Try the integrated integral for this inside integral first. In this case, it's x squared y. Well, yeah, that's just a polynomial. Polynomial is pretty straightforward to integrate, fortunately. So we're going to get x squared y squared on 2 after doing integration with respect to y. And now we want to plug all our values in. So I'm going to take this I'm going to factorise the half right out. Makes it a little easier to write down. So I plug in the 2x plus 1. I'm getting x squared 2x plus 1 all squared. Minus, then plug the x in, go to x squared times x squared minus x to the 4. Now you have to try to integrate this expression. So I've got a product here, and x to the 4 is fine, but you've got a product. What you really have to do is you're going to have to expand this out just to give a chance of really integrating. So you're getting 2x all squared, so it's going to be 4x squared times x squared, so x to the 4, plus 2x plus 1 times, so 2x times y 1 times by 2, so it gives you 4x, another x squared chucked along the end, and 1, which gives you an x squared. And then the minus x squared will cancel out one of those 4s, and you're left with just 3 of them. So you might want to put another line of working down. That's quite acceptable, of course. And I've still got my half. Then integrate normally. So the integral of 3x4 is going to be 3x to 5 on 5, etc. So on 4. And again, it's worthwhile you trying to work this out yourself rather than just look at me do it. But again, limits for 1 to 3. And we sub the numbers in. So we half, plug the numbers in, so you get 3 to the 5, so 3 to the 6 on 5, plus 3 to the 4, plus 3 cubed, which is 27 on 3, which is just going to be 3 squared, and then minus everything with 1s in it. So 3/5, I can sub in 1 easier, plus 1, plus 1/3. And I would use a calculator at this point in time to help simplify it down. That gives you a basic idea. So, as you can see, with this sort of cases, you've got to make sure you put the limits down on. So you've got to work out the limits. And then try the inside integral first. If it works nicely, fantastic. If it doesn't, that's when you consider swapping the order of integration around. This is the last one, where the region was not given, where the region integration is not given by limits directly, and not given by a bunch of equations, but given by a picture. And so the trick of this bit is to try to translate this picture into some sort of equation sort of thing. And you can do it this various ways. So you're going, well, I could get the colour right. Specified as being between two curves, so therefore x is equal to this top curve here, which ends up being the square root of 4 squared minus y squared, and then bigger than the bottom curve here, which you could write down as 1 squared minus y squared, and then the y value is everywhere from all the top of 2 down to, which should be minus 2. So you could specify limits that way. And I mean, if you persevered, I'm sure you could get the answer too. But whenever you've got circular regions, it's better, I find, it's quicker not to do that one, but to use polar coordinates instead. Now, why did I mention this other thing? If we're going to say polar coordinates, well, if you ever get expressions like square root of 1 minus y squared or square root of 4 squared minus y squared, that's the key thing going, hold on a sec, they're circles. And whenever you've got bits of circles, change it to polar coordinates. That really makes it easier to do. So when you've got polar coordinates then, we have x is r cos theta, y is r sine theta. Now if you had the expression x squared plus y squared, well that'd just be r squared. So we don't have it, but that sometimes is a saver. And dA, so a small amount over area, is the thickness times by a small bit of arc length, which is r d theta. It ends up being r d theta. And we just have to work out what the limits are. So we've got the radius, that's the radius. Well, the smallest radius gets is 1. The biggest it gets is 2, so that's what the limits for it are. And theta, so it goes all the way down to here, which is an angle of minus pi and 2, and the largest it gets is all the way to the top, which is an angle of pi and 2. So therefore our integral now becomes the integral of, well, x, which is r cos theta, y, which is y squared, which is r squared sine squared theta. And dA becomes r dr d theta. Instead of written this way, I should write down the limits for r first. So r is between 1 and 2, and theta is between minus pi and 2 to pi and 2. Make it black. So in this case, this integrand's, although it's got lots of things in it, you can see it's just a product of things of r, things of theta. So we can actually separate it out. And when you separate it out, you can actually separate it out completely. So I can put all the theta bits together. So cos theta sine squared theta d theta. And I could put all the r bits together. So you know, from 1 to 2 of r squared r, because you know the 4 dr. So I've just, it's called this case it's separate. It's separable because it's just a product of two functions, one of which is completely one variable, function of completely other variable. So it's separable. And again, you might have seen that trick of separating stuff when you're doing differential equations, for example. So it's useful because it really just makes things into two single integrals straight away. And then just do them separately. So the second integral is the 5 on 5 between 1 and 2. What about the first one? If you plugged minus theta into here, you've got square. This is a cos minus theta is cos of theta. So you might notice that it's actually an even function. And so what you can do, because it's an even function, you can just do the integral from 0 up to the top one and just double it because it's even. Now, if you did notice that, you still get the right answer, of course. It makes it easy to write down, so that's what I'm going to do. To integrate cos theta sine squared theta, you go, well, just a single integral, what can we do? Well, this is when we have to think about your bag of tricks for integration. And you're going, hold on a sec, I can just do substitution here. So I go, well, I've got an function of a function, so sine theta all squared. I can let u equal sine theta, and we'll clean it nicely. Or you can do it by observation even. You go, oh, hold on a sec. Well, the derivative of sine theta is cos theta, and so that just comes down the front. And so I can see that really it's really just something like the derivative of sine cubed, something like that. So if you take derivative of sine cubed, you'll get 3 sine squared theta times by the derivative of what's inside, which gives you cos theta, which is almost right. So therefore, we just got to divide by that 3 there just to make sure it matches up properly. So that's what we call integration by observation. Substitution would be fine too. But again, use your bag tricks. The 2 comes down, and then we want to integrate this between the limits of 0 to pi and 2, as I've written it down. So sub in pi on 2, sine of pi on 2 is 1, cubing it still gives you 1, so it gives you 2/3 of 1. Sub in 0, you get nothing. And then sub in 2 and 1 in this one, so 2 to the 5 is 32, and sub in 1 you get 1. So putting it all together, so 32 minus 1 is 31, so you're getting 2 lots of 31 is 62 over 15, so thereabouts as our final answer. So just recapping, when trying to face with double integrals of various sorts, look at what the region of integration is helpful. If it's anything based on circles, or annuluses like this one here, polar coordinates is good. You can see it maybe visually. If you can't, you've got this sort of square root expressions. Otherwise, just try the inside integral first. If it's doable, fantastic, and you're home, and you're home almost, and you'll be home pretty quickly. If the inside integral gets difficult, try considering swapping order of integration down. If the region of integration really is complicated, then other tricks available is to transform the region. But in the exam in this sort of situation, you would be directed to do that, and I'll do that separately. So I hope that helps just give you a sense of when you look at integral, what sort of techniques you can employ and how to actually do it as well. Thanks.